Okay, I'm very happy to introduce Ari Shnidman for our penultimate members colloquium this year. He's going to tell us about Selmer groups and Hilbert's 10th.
For the invitation. That's very nice to be here for the year. Yeah, so I'm going to talk about Selmer groups and Hilbert's 10th problem. So Hilbert's 10th problem is a question about Diophantine equations, and is there an algorithm that can tell you whether a given Diophantine equation is solvable or not, has solutions or not. Selmer groups are just a very general tool in number theory. As we'll see, they're helpful for certain algorithmic questions of a similar flavor. And I'm going to do a kind of a survey, more really about Selmer groups than about Hilbert's 10th. The Hilbert's 10th will come in at the end as an application. Selmer groups are kind of a cohomological tool that show up in number theory all over the place. And it's very formal and hard to get into if you're not a number theorist, I would say. It's in terms of Galois cohomology, group cohomology. And so I'm going to attempt to kind of, this is more a talk for the non-number theorists, and I'm going to attempt to give kind of a geometric way to think about Selmer groups. So let me start with a motivating question. Well, I'll first start with a question we probably all know the answer to. So which integers are of the form x squared plus y squared? Here, we can let x and y be rational numbers or integers. It doesn't actually matter. And so we probably, most of us, all of us know the answer to this question. It has to do with how you factor n. And when you factor n is for the primes that are 3 mod 4, you need an exponent of 2, or more generally an even number in the exponent. And that's an if and only if. So this is maybe due to Fermat. I don't know if Fermat really proves that, but the statement is due to Fermat. So this is a very old question, and there's a very simple answer. It has to do with congruences. There are congruence conditions on n that tell you the answer. There's a simple rule that tells you the answer. So now I'm just going to change the 2 to a 3, and now we have not only an open question, but we have a question that doesn't have an answer. So I claim that there is no good rule to tell us when n is the sum of 2 rational cubes. Arithmetic of n is relevant, and I will not go into it. This is a very subtle thing. Root numbers, elliptic errors, blah, blah, blah. It's relevant, the arithmetic of n, but I claim that there is no simple rule, or really any rule involving the congruences on n that will tell you whether it is a sum of 2 rational cubes or not. Really, one should view this more as a question about randomness. There's some random process that will tell us whether n is a sum of 2 rational cubes. And the question is, what can we say about that random process? And well, we're never going to answer this question. So let's change the question and ask how many? Well, okay, of course, the answer is infinitely many, but what I mean is proportionately. So what proportion of integers, as you let n go to infinity, is the sum of 2 rational cubes? That's a question we can ask. We can throw it into a computer. And if you look far enough in a computer, you'll see it. Well, actually, I'm not sure you would actually convince yourself of this conjecture, but here's the conjecture. There's a conjecture that the answer is very, very simple. It's 50%. So that's the conjecture, and nobody's written down this conjecture, as I've seen explicitly. It's more of a special case of a more general philosophy due to Katz, Sarnak, Goldfeld, Kuhn and Rans. There are actually multiple ways to kind of get at this conjecture. And one way is via Selmer groups, and I'll try to explain why in the talk. But first, I have to explain something much, much more simple. This is more like fodder for the number theorists. And it's also just a beautiful conjecture that it's just a coin toss to whether, n is a sum of 2 cubes. But we first have to address the much, much more simple question of, for a given n, is n a sum of 2 cubes or not? Even that one question is completely not clear to this day. There is no provably known algorithm to answer that question. So we need to step way back. So here's an algebraic fact that you can work out on your own. I will not attempt to do it here, but this equation has solutions in the rational numbers. So I fixed n. if and only if this equation has solutions. So this is some arithmetic that you can work out. And really what we're asking is, does this equation have a solution in the rational numbers? We fixed n. This is an equation of an elliptic curve. So we'll work in the more general setting of elliptic curves. So more generally, with EAB, it depends on two parameters, be an elliptic curve. So here, A and B, these are rational numbers. And let's call this cubic polynomial f. And I want to assume that the curve I get is smooth. So I assume that the discriminant is not zero. So it means that the cubic polynomial has three distinct roots in the algebraic closure. And I'm going to think this is a plane curve. It lives in the plane, x and y. I think of it as actually something in projective space. So I compactify by making it homogeneous, adding a third variable. And we get this extra point when I view it in the projective space. Infinity, there's only one extra point when z equals 0. And in fact, going back to the Greeks, they wouldn't say it this way, is that E is an algebraic group in a natural way over Q, over its field of definition, with identity element infinity, which we'll now start calling 0 often. And as again, probably many of you have seen this, the way you get the group structure is you just declare that any, I'm not going to, okay, if we draw a picture, maybe it looks something like this. You declare that the sum of any 3 points on the elliptic curve that lie on a line, so any 3 collinear points is 0. And that determines a group law. And so the consequence is that the set of rational points forms an abelian group with identity element infinity, but it's really, so this is an abelian group. But it's really a stronger statement than just this. Right? So I kind of told you what characterizes the group law. The way you add 2 points is you draw the line between the 2 points, you find the third point that hits the curve, and that's the inverse of the sum of the 2 points. But what the stronger thing here is that this group law is defined by algebraic equations, by rational functions, and those rational functions have coefficients, so it's ratios of polynomials, and those polynomials have coefficients in Q. So that's why when I add 2 points with rational coefficients, I get another point with rational coefficients. And more generally, if I take a field extension, then the F valued points of E will also form an abelian group. And from if we view the elliptic curve as a Riemann surface, we look at its C valued points, then you will get a torus, which kind of explains the group structure, a complex torus. And this isomorphism tells you something about the group structure. For example, it does tell you a little bit about the torsion possibilities for this group, but it doesn't actually tell you very much. It tells you that this is some abstract subgroup of this, but this is a huge group, infinitely generated. It's not clear what the image of this and this is, but we have a structure theorem through the Mordell and Vey. This was Vey's PhD thesis. His contribution is, in fact, more about the higher dimensional case. But the theorem is that this group is finitely generated. So it's not just an abelian group, it's a finitely generated abelian group. And we can then talk about the rank. So the rank is the rank as an abelian group. So that's this integer R. So this we'll call the rank. The elliptic curve here, this is the torsion subgroup, which is a finite abelian torsion subgroup. And generally speaking, most elliptic curves over Q have trivial torsion subgroup. And so as an example, let's call this elliptic curve En. It depends only on n. And let's restrict to n at least 3 and cube free, which is, we might as well just do this for our problem. So then this is if and only if the rank of En is greater than or equal to 1. It just turns out one can compute, it's not hard to compute torsion points on elliptic curves, that these elliptic curves under these conditions don't have interesting torsion points. So T is trivial, and the only interesting rational points, in other words, other than the infinity, are infinite order. And what we're really asking is the rank bigger than 1 or not? And the conjectures would say more precisely that 50% have rank 0 and 50% have rank 1. Not just rank greater than or equal to 1, but exactly rank 1. And that's a more precise version of this conjecture about the ranks of elliptic curves. Okay. But of course, just again, going back to the more basic question, how do you decide whether the rank is positive or not, whether there are any rational points or not? That's where Selmer come in. So the question in general now is, how do you find R? How do you figure out what R is? Okay, so this is where Selmer groups come in. And yeah, so I'll give you the geometric intuition for them. I can't give exact definitions of everything without going into Galois cohomology, and I don't want to do that. So I'll give the geometric intuition. And by the way, this is also the kind of how you prove the Mordell-Weil theorem. It's also, you'll see, a little bit why this is a finally generated group as I talk about Selmer groups. Okay, so yeah, so fix n, and what we're going to do is we'll look at just the n torsion points on our elliptic curve. As I said, torsion points are kind of easy to compute when you have an elliptic curve. So we'll look at the n torsion points. So these are q such that n of q is infinity or 0. And as a set, this is a subgroup, of course, of order n squared. You can see this from the torus description. But notice I'm not insisting that they have rational coordinates. And so these points may not have rational coordinates, but the original curve is defined over Q, and the map, which is multiplication by n, is defined over Q. And so its kernel should be defined over Q. And that means that you'll have an action of the Galois group, Gal Q bar over Q, acting on this group, which is abstractly Z mod n squared. So this is not just a group, it's a group Z mod n Z squared with an action of the Galois. And here's the tiny bit of group cohomology, Galois cohomology that I'll use. I'll just make it a definition. So I define H1QEN to be the set, or it's really a group, but for now we'll just say set, of EN torsors up to isomorphism over Q. And this is kind of the objects here are kind of concrete. What is an EN torsor? I just mean a finite set with an action of the Galois group and with an action of EN on it, which is simply transitive. Everything needs to be defined over Q. It just means that the Galois action needs to respect this action. And this is a thing you do all the time in Galois cohomology. You can parameterize all of the possible isomorphism classes of such torsors up to isomorphism. And it turns out they form an abelian group. And I'll kind of just show you with examples what the abelian group is in certain examples. And we'll just believe me that there is a natural group operation on these isomorphism classes. Here's just the simplest possible example. Not even of elliptic curves, just of this torsor phenomenon. So what if I put here the group Z mod 2Z, and here the action of the Galois group is trivial. So there's no interesting Galois action that acts trivially on both of the non-zero elements, both elements. And here it's easy to see that either with the correct definition or kind of even informally, that this is isomorphic to the following infinite group, but very simple to understand group, the group of all square classes in Q. And you get it just by looking, associated to a square class, the torsor maybe I'll write it this way. The solutions to the equation x squared minus d equals 0. Right, there are two solutions to that equation, and Z mod 2Z acts on those two solutions by scaling. Everything respects the Galois action. There's a non-trivial Galois action on the two solutions, but you can write down this, you get a simply transitive action and it respects Galois, and this is the isomorphism. Okay, that's for this group. Of course, it can happen sometimes when you take n to be 2, that we can even write this. So if it happens to be the case that even as a group, or as a group with an action of the Galois group, that this is Z mod 2Z. In other words, let's say you happen to have two independent two torsion points on your elliptic curve, which happens exactly when F splits completely over Q, then this H1 will be abstractly isomorphic to the square of this group. You have two copies of this and you get this. Okay, so far this is just abstract nonsense. But the point is that we know nothing really about the rational points on the elliptic curve. That's the whole problem. We don't have access to them. But we're gonna anyways define a map from there, from this group of rational points to this space, this group parameterizing torsors. Yeah, I should say, I didn't explain what the group structure, the abelian group structure is on this, but there's a distinguished element, an identity element, and that is En itself. En acts on itself just by translation in the group law. And so that's, I won't go into the group structure. I mean, you see it kind of clearly here, what the group structure is, but at the very least, we know what the identity element is. It's En itself. Okay, and so here's the crucial definition. This is the Kummer map. This is where the geometry comes in. So we'll define this map, the Kummer map, which associates to a point a En torsor, and which En torsor it will associate to the point Q, the preimages of Q under multiplication by n. And so the picture here is you have E covering itself via the endomorphism multiplication by n. This is a degree n squared cover of Riemann surfaces or algebraic varieties over Q. I will draw it by caricature. So we have infinity here, we have Q here, and then I'll draw, this is the case n equals 2, so it's a degree 4 cover. I look at the preimages. Infinity is one of the preimages. In general, the preimages are the two torsion elements. This is a group homomorphism. So any fiber, in this case, this fiber, is going to be a torsor for the kernel. So this acts on this simply transitively. And so individually, these points need not be defined over Q, but as a set they are, because this one was defined over Q and this is defined over Q. And they even have this extra structure of being a torsor under E2 in this case, but this is just a character. This works for all of them. Okay, and now we stare at this for a little bit. And first we observe that, in fact, this factor through E of Q mod n E of Q, because if you're a multiple of n, if Q is a multiple of n, that it means that one of these points is rational. And that means that it's the trivial torsor, because once you have a rational point, then by sending infinity to that rational point, you get an isomorphism between the trivial torsor and this torsor. So you actually get a well-defined map from this quotient to here. And for basically the same reason, it's even injective. If I happen to know that this torsor is trivial, well, then the only torsor with a rational point is the trivial one. And so there must be a rational point. And here that means that Q is a multiple of n. And so what we've done is we've embedded not the full group of rational points, but its quotient by n into this abstract group. And the point is that the size of this group is related to, this is Z mod NZ, roughly speaking, this is Z mod NZ to the R, where R is the rank. I'm kind of ignoring the fact that there might be some torsion in E. Most of the time there isn't. Okay, and so we're going to try to study this by studying its image in here. The problem is that this is infinite and this is finite. by the modality, but this is infinite. And so we need something much smaller. In fact, before that, let me just give one example, because the part of the point of this is that you can turn this into an algorithm eventually when I'm done explaining it. This is all really explicit and concrete. So maybe I'll do it here. So example, let's just do n equals 2. Like, what does this actually look like? It's very simple. So let K be the cubic algebra, which is just Q into an X mod f of X. And let's let theta be the image of X in here. I guess this is, in that case from before, the trivial case, this would be 3 copies of Q as a product of fields. But this could often be a cubic field, but it's some 3-dimensional Q algebra. And let's just, okay, so first of all, in this case, you go and you check. I won't go into the formalism, but you check that you get something which is square classes in K, but then you also need to kill all of the square classes that happen to be rational. This is a concrete thing. We're just looking at square classes in K, and okay, we also killed some other classes, the ones that are rational. And the map is, here's the Kummer map. It just sends X naught, Y naught to X minus theta, X naught minus theta. And yeah, so Castle's called this the X minus T map. So the amazing thing is that the people who developed this did not think in terms of Galois cohomology and group cohomology. They did it with their bare hands using explicit equations. And the point, and I think this something has been lost in that process, so only thinking about it formally. The point is that we're translating the geometry of the elliptic curve into field arithmetic. It's a way of trying to translate geometry into field arithmetic. This is just field arithmetic. Okay, so similarly for any n in principle, you can just do something as explicit as this. Of course, for n really large on a computer, it will take forever. For n too large, but for small values of n, it's practical, and it's a thing one can do. Okay. But as I said, so far not helpful in saying anything about the rank. Oh, I'm gonna just go back here for a second. The way we make it helpful is we observe that there's nothing really special about doing this with the field Q. You can do this for the field QP for every prime P, including the infinite prime, in which case QP means R. You have the same picture, and it's all compatible. So Q is contained in QP, so I have a map like this. And if I have a torsor over Q, I just think of it as a torsor over QP. So you have a map like this. Let's call this restriction map, and we'll call this del P. And the Selmer group, I mean, the observation now is just that we don't know what this is ahead of time. That's the whole problem. We're going to try to think of its image in here. One thing we know about its image in here is that when I go down here, it has to come from the image here because this square is commutative. So we'll just focus on the subgroup of this that locally, in other words, when I restrict to QP, it comes from here. That's the idea. That's the definition of the Selmer group. I'll still write it. So the definition is, this is those En Torsors such that for all P, including infinity, when I restrict it, when I think of it just as a torsor over QP, an En torsor over QP, it's in the image of del P. This is a subgroup of the bigger H1, but the key point is that it's finite. This bigger H1 is infinite, but this guy is finite. And then the even more crucial point is that it's computable. And if you don't like QP or whatever, like I'm not going to say much more about QP. That's not really the point of the talk. The point is that this is a finite group. And even this is a finite group. And you can just do these computations with your bare hand for small enough p, for any number, finite number of p. It amounts to doing modular arithmetic. You're just looking at solutions of the elliptic curve over fp instead of q, which is easy. If you're a computer, you just search through all the possible points and you do some field arithmetic computations, and you end up with an answer of what is the image of this in here for all small enough p. Obviously, you can't do it for infinitely many p. And then the magic is that for large enough p, you know ahead of time what the answer is for whatever reason that I won't explain right now. And so this ends up being completely computable, this Selmer group, the global classes that happen to live in the image of this del p for all primes p. Okay. And what's the point? Well, so first of all, by construction, this group lives inside of the Selmer group, the hidden Selmer group. And let's write it in the form of an exact sequence. So this includes into this. This is finite and computable. So you get a bound on how big this group is. And I don't want to define the Tate-Schaffer-Hilbert group of an elliptic curve in this talk. It's really not necessary. The more important definition is this, is we define this to be the co-kernel of this map. So this is just measuring the abstraction to which, are there elements in the Selmer group that actually don't come from rational points on an elliptic curve, which is a crucial question if we want to understand, maybe this is finite of order 4, but maybe this is trivial. And then we still wouldn't know whether there are rational points or not just from staring at this finite group of order 4. But what you at least get, so that has to do with the subtlety of whether this group is 0 or not. But what you at least get is an inequality. You get that, let's make sure. What do you get? You get n to the rank is less than or equal to the size of this group, just from this inclusion. If p is a prime, then you'll get that the rank, or if n is a prime, p, then you'll get that the rank of E is less than or equal to the dimension over fp of the Selmer group, the cell p. Okay, and why is this nice? It's nice because we now get an algorithm. Almost. So we get an algorithm to find the rank on an elliptic curve. Here's how the algorithm works. Okay, so algorithm. So this is only a conditional algorithm, whoops, as we'll see, to compute the rank of an elliptic curve. How does it work? It's one of these by day, by night algorithms. You do kind of alternate doing two things. So by day, you compute Selmer groups. So compute the size of some L, some N Selmer group, and you probably want to start with N equals to 2. And so maybe we compute the 2 Selmer group, N equals to 2. One thing that could happen is that we get 0, that it's trivial. There's only one element, the identity element. Then we're done by this inequality. This group is trivial, so therefore the rank is 0. Okay, but another possibility is that you compute this, and it's not trivial. It has size 8. So potentially rank 3. So then you now switch gears. So by night, we just search naively. Search for points naively. In other words, plug in random values of x and y of bounded height and just see if they give you a rational point, and just do it a lot. Because maybe we got 8 as our answer when n equals 2, 2. So we expect that there could be 3 independent rational points. So we just start looking for them. Maybe we find 2 independent rational points. So then we have them with our hands. They're in front of us, well, on our computer. And so we know that the rank is at least 2, but we can't, we search, we can't find more. So now we go back to the day and we go to n equals 3. And we do it again, compute the 3 Selmer group, we'll get a potentially new inequality. And again, there are 2 things that could happen. It could be that you get 9 for the 3 Selmer group. Then this, we know that the rank is at least 2, so then you get a strict inequality and you're done. The rank is equal to 2. But again, it could be that we get the rank, this size is 27, and that we're not sure still whether the rank is 3 or 2. And so then you just keep searching. And if you never find something, you go back to n equals 4. You do it again, and you keep going. And the point is that as long as this Tate-Schaffer-Avich group, this co-kernel, is 0 for some n, we win eventually. Because for that n, we're going to get a sharp inequality. And so as long as we just search for points, we'll eventually find them and we'll be done. Of course, we're going to be alternating. We're going to do this alternating thing, even if we've passed n, the n that works. So it's a little awkward, but as an algorithm, that's fine. And now, why is it a conditional algorithm? Because we don't know whether this is true or not, which is this kind of mind-blowing fact. If you know a little bit more about the Tate-Schaffer-Avich group, it's kind of mind-blowing that for a given elliptic curve, we don't know that there's at least one n for which the n torsion in SHA is the Tate-Schaffer-Avich group is 0, but we do not know that, and so it's only a conditional algorithm. It's conditional on the conjecture. This is part of the Birch-Swinnerton-Dyer conjecture. This is, a more general conjecture that Tate-Schaffer-Avich group is finite. But I didn't introduce the Tate-Schaffer-Avich group, so let's just say that, let's put it this way. The P torsion in the Tate-Schaffer-Avich group is 0 for primes P large enough. So if we believe that conjecture, then we have an algorithm. Of course, we are free to believe the conjecture. And so in your computer, Magma or Sage, they'll essentially run this algorithm, obviously optimized in various ways that I'm not going to talk about. Okay.
But Magma or Sage or computer algebra packages can't compute, and Selmer groups are large, and can they?
Yeah, so, well, no, they can in principle. There literally is an algorithm that I don't know what is encoded into Magma or Sage, so I don't know the functionality of Magma or Sage, but I could do it with my bare hands. I would never want to, but yeah.
Is there any limit of the computer time needed to?
Oh, there's a huge, yeah. So, I mean, if you believe more sophisticated conjectures, then for every n, there's an elliptic curve whose Tate-Schaffer-Avich group is non-zero for all the n torsion, and is non-zero for all n not less than n and not equal to 1. And so in principle, then you would have to go out to, and so and even just forgetting that, just the number of fields that start getting involved start becoming very big. This is a cubic field. N is 2. If I took n as 5, I think I get like a degree 125 field or something for n equals 5. So yeah, you'll in practice, there are all sorts of tricks to make it much more efficient than what I'm describing. But just an abstract algorithmic, the question of is there an algorithm? This is enough.
It's exponential.
Oh yeah. I mean, there are questions of class numbers you have to think about if you want to actually understand the complexity, but yeah. Okay. Now, in principle, there's an algorithm. What would be really nice, there's something very unsatisfying right now about this algorithm, which is the by night part. The only way we have to find rational points is just by searching naively. It would be much nicer if there was a way to produce the rational points for us. Or given that we have the technology of these Selmer groups, it would just be nice if there was a way intrinsically in terms of the Selmer group to figure out whether this is, whether all of the points in here, everything in here goes to 0 when you go here. And amazingly, I won't go into the conjectures. This has to do with Cassels-Tate pairing, and here you really need heavy Galois cohomology. But amazingly, they're conjecturally, you can determine the rank simply by looking at Selmer groups for large enough n and using something called the Castle's tape parent, assuming, you still have to assume this conjecture, assuming the finiteness of shell. What I will write, so I can't formulate that, it's too complicated to formulate, but here's just a simple version of it, which is, so even this is strictly speaking a conjecture, but a lot of work on this. So suppose, just for simplicity, this is not like a serious assumption, that there's no p torsion on your elliptic curve. And suppose that the dimension of the Selmer group, the p Selmer group, is 1. So the Selmer group has size p. Then the rank is 1. Okay? And the point is, conjecturally, this is supposed to be the square of an abelian group. Again, I can't explain where that comes from in this kind of talk, but that's part of these conjectures. And in particular, as an FP vector space, that obstruction has to have even dimension. And so if the Selmer group is one dimensional, this has to be 0, and then you know everything comes from rank. So this is one example of what I was talking about, where sometimes from staring at the Selmer group, you actually can say, oh, there are rational points. Well, this is a conjecture, but this is known in many, maybe in some sense most cases, but it's still not quite known in all cases. This is an active area of research, so work of many, many people. I mean, this is kind of, these are the people who kind of finish off various cases, but this relies on many things, including Fermat's last theorem, so Andrew Wiles' proof of Fermat's last theorem, et cetera. So there's a lot of math that goes into even just cases of this conjecture. The point, though, is that sometimes just from staring at the Selmer group, well, you certainly can upper bound the size of the rank, but you can even lower bound sometimes in appropriate situations. Using this, I mean, this uses lots and lots of heavy Iwasawa theory, the Grossage formula. So this is there's a lot of stuff that goes into this. Okay, so I'm going to transition to the Hilbert's 10th, but maybe I'll just give a theorem to answer partially the original question that we started with, which is what proportion of integers are a sum of two cubes and what proportion are not. So this is from a few years ago. And it's really, but it was been improved recently. And so I'll just write it as a combined result. So, long duo. And it says that at least 47% of n are a sum of two cubes. Sum of two rational, are not sum of two rational cubes. And at least, I think it's like 9.5% of n are. Yeah. And the way this is proved is by using Selmer groups. You have to study the Selmer groups kind of on average as you let n vary. And this result, for example, is considering n equals 3 Selmer groups. And this result comes from n equals 2 Selmer groups. So this was n equals 2, and this is n equals 3. And the n equals 2 gave us some proportion, but then when you also do n equals 3, you get an even better proportion. And I'll just say very quickly, I'll discuss the first step of the proof for n equals 2. So the first step, first step is you look at the two Selmer groups of these elliptic curves that are relevant to the sum of two cubes problem. And in fact, you could take a step back and just look at all elliptic curves. And then you have this result of, you have this goes back to Birch, Fringe, and Dyer, Castles, that if I just look at over all elliptic curves, and I look at all of their two Selmer elements, then this you can think of any two-Selmer element as a binary quartic form. And it's really an orbit of binary quartic forms. So sim4q2, this just means a quartic form in two variables, so degree 4, two variables, homogeneous. So I'm thinking of it as it's the fourth, was b x cubed y plus e y to the fourth. And this should be reasonable because what is a two-Selmer element? It's an E2 torsor, which is ultimately just 4 points with certain properties. And the roots of this thing give you 4 points. And you check, I mean, this is kind of even this bijection is not trivial. Not all E2 torsors come from a polynomial like this, but you check that in fact, yeah, there is a bijection like this. And here I have to start making little caveats like solvable binary quartics, so they have to satisfy certain congruence conditions. I also want to say something like non-degenerate. I don't want the discriminant to be 0. And then what Bhargava and Shankar did, they consider the average size of the two-Selmer group in overall elliptic curves, is you use this bijection and you try to count. You try to count orbits, integral orbits. I should maybe also say integral. So represented by binary group forms and integer coefficients. You just try to count integral orbits under the action of PGL2Q. And I say just, but there's a lot of work that goes into this, and you can ultimately estimate the number of such orbits with bounded invariance A and B. A and B are exactly the two invariants for PGL2 acting on binary quartics. In our case, we're just setting A equal to 0. This is not actually what we did in our paper. In our paper, we used the parameterization of Bhargava and Ho to do this, but for exposition, you could prove it this way. You set A equal to 0. This amounts to putting a condition where there's a certain quadric in this space that vanishes. And again, you try to count. And I'm completely not talking about how you do that count. In this case, in our case, you'll have to use the circle method. When A equals 0, we're basically recovering the elliptic curves En from before. So this point of view of Selmer groups allows you to translate the problem, not about rank, but about the size of Selmer groups to objects that we can understand. But then using that, you show that there are not very many Selmer elements. The average size of the Selmer group is 3, as it turns out. And because the average size is 3, a lot of them have to have rank 0, and a lot of them have to have rank 1. The ones that have rank 0 give you these guys, not with such a high proportion, but something. And then the ones with rank 1 combined with this conjecture, the converse theorem, gives you these guys. Okay, that's a very rough sketch. Now, let me transition to Hilbert's 10th, which is basically the opposite problem. So what this is showing is that for curves, elliptic curves at least, there should be an algorithm. Maybe it's only conditional, but we expect that there is an algorithm to find the solutions. Hilbert's 10th problem is just about any Diophantine equation. Is there an algorithm that, given a polynomial, tells you whether there are solutions in the integers to that polynomial set equal to 0? And it was proven in the 70s by Matyasiewicz, building off of work of Davis, Putnam, Robinson, that the answer to that very general question is no. So there is no algorithm to determine solubility of polynomial equations over Z, over the integers. It's still not known actually over the rational numbers, whether there's an algorithm or not. But they showed that at least over the integers, there's no algorithm. What they're really showing though, this sounds like a very negative result. What they're really showing is a positive result. They're showing that, this is what they really show. Matyasiewicz is fine. He finished the proof. This was in 71, 63. So what they really show is that all listable sets, in other words, sets that could be spit out of a Turing machine. There's all the set, this is a listable set is just any set for which there exists a Turing machine, such that when you run it indefinitely, it spits out that set. They show that all listable sets are Diophantine, meaning that there is some polynomial with possibly many variables with the property that when you just look at that first variable and you ask which inputs to the first variable have the property that there exists a solution by filling in the rest of the variables. And a set is Diophantine if there exists a polynomial that has that property where you put in the inputs S into the first variable, and it's exactly those inputs that give you a solution. And this is what they show. This is kind of, to me at least, I'm not an expert in this kind of logic or model theory or whatever, but this is kind of an amazing theorem saying that Diophantine equations capture the complexity of Turing machines. So that's what they're actually showing. The point is that it is known that there are plenty of listable sets for which there is no algorithm to output whether it is in the set or not in the set. And so that's how you deduce the theorem from that, what they really show. How do they show it? I'm not going to, I was hoping to learn a little bit better on a conceptual level to understand a little bit better what's really going on in that proof. The proof is elementary in a certain sense, doesn't use lots of heavy machinery or anything. What I'll just say is that the proof, so this is the second part of the remark, the proof uses the solutions to Pell's equation. This is a very inadequate summary of their proof, but this is kind of one of the key things that their proof uses. I mean, what you're trying to do is you're trying to show that any procedure given by a Turing machine can be encoded algebraically. So one of the main steps is using the infinitely many solutions to Pell's equation. Here D is some positive number to show that you can do this. That's the algebraic equation that they used to get Diophantine on a very kind of basic level. Okay, so the question one question is, as I said, is this true over Q? Still not known. Another question is, what about other rings in which we can do computation? So what about, so this is a question, a response to the theorem. So the theorem is true over C. What about over other rings? R, and specifically, what about over rings that are finitely generated as rings, as the algebras? Now, there's a huge caveat you have to put in if you ask about finitely generated rings. Namely, you should demand that they're infinite finitely generated rings. So what about other rings, say, finite rings? If it's a finite ring, then there's definitely an algorithm. So you just have to exclude the infinite, the finitely generated rings. And here, this is this recent result, and this was proved by two different groups. Both use Selmer groups. Selmer groups for different curves, but both proofs use Selmer groups. And yeah, the theorem, it says Koymans, Pagano, and then separate proof, Malboj, Vargava, myself. And so again, the theorem, let me not write it out, but again, no such algorithm for these infinite finitely generated rings are. Let me not write this because I'm running out of time, but Mazur and Rubin about 10 years ago had given a conditional proof of this, conditional on the finiteness of the Tate-Schaffer-Davidge group, so conditional on the types of conjectures. So they also approached it using Selmer groups, but this is an unconditional proof. Now,
And do you get the same complement, positive sign?
Say it again?
Do you get also that?
Yes.
Recursive.
Yes, and so, yeah, let me say, what are we really proving? Just like over there, like what is really being proven? It's a positive result. It's not really a negative result. We're proving that, so theorem, it's really what it implies this. So same authors. The theorem is that, well, there's a reduction here. You can reduce to rings of integers of number fields. This R, one, that's not obvious, but this was shown in Kirsten Einstrangler's PhD thesis, that you can reduce to rings of integers of number fields. So let K be a number field. And OK, it's a ring of algebraic integers. The analog of Z inside K, ring of integers. So then what's really being proven is that Z is Diophantine inside OK. So what does that mean? That means that there exists a polynomial with coefficients in OK, in possibly many variables, such that when you look just at the first variable and you ask which are the inputs such that you can fill out the rest of the variables to get a solution, it's exactly the set of integers. And when I say inputs, I mean over OK. You're considering all the possible, not just in Q or something, but over OK. And you can cut out the integers inside of OK using a polynomial, using a Diophantine equation, which again is to me surprising. And this should have other consequences for the model for set theory. This has other consequences beyond this negative result. I don't really know all of the different consequences, but this is kind of just a basic fact about the logic of OK. It contains Z as a Diophantine subset. Now, in the last 3 minutes, I need to explain what does this have to do with Selmer groups or elliptic curves. So this theorem, the question has been worked on for many years. Even Julia Robinson in her work, she apparently, something Wei told me, she was played around with, instead of using a Pell's equation, but using an elliptic curve for the original Hilbert's problem. And it's been known for a while that you can reduce the question of is Z Diophantine inside OK to a statement about elliptic curves, or more generally abelian varieties. So this is a theorem of Schlappentoch. So it involves a certain condition, we'll call it star. So suppose that for all quadratic extensions, K over F, there exists not necessarily an elliptic curve, but it will be even more broad, an abelian variety. An abelian variety, A over F, such that, this is quadratic extensions of number fields. So that all of the fields here are number fields. They're finite extensions of Q. So there exists an abelian variety over F such that the rank of A is equal to the rank when I view it over the larger field, the quadratic field, and they're both positive. And okay, this is one of these riddles. Oh, let me finish the theorem. If star holds, then for all number fields, well, Z is Diophantine inside of it. And so in particular, you can conclude, if you can verify star, you can conclude that Hilbert's problem has a negative answer. And so it reduces in a way that's kind of similar to this Pell's equation reduction. It reduces the question of can I define Z inside of OL to just a statement about algebraic groups, in this case, abelian varieties. Abelian varieties, elliptic curves are the one-dimensional version of it. And this is a riddle, which the answer is obviously yes, there exist these abelian varieties, but it's actually really not clear how to prove it. It took many years. Maser and Rubin proved it, but only assuming this conjecture about the Tate-Shopper image group. And this is what we prove. And I'll just write down the abelian varieties that we use. And what we do is we use Selmer groups. So I'll just write down the theorem. So we use higher dimensional abelian varieties. This other group, Koymans and Pagano, they use elliptic curves. But if we want a statement that just says that star holds, we should use our result. So this is the same set of 4 authors over there. So star holds, and it even holds if you just look at the abelian varieties Jn. So this is the Jacobian of the curve Cn, where Cn is the curve y squared equals x to the L plus n. L is an odd prime and arbitrary element of the ground field S. Let's say non-zero. Now, I didn't say what Jacobians are, but it's very easy in this case to say, at least over the complex numbers, what this Jacobian is. Jacobian of a curve is essentially the smallest abelian variety that the curve embeds into. So this is a curve of genus G equals L minus 1 over 2. It's a hyperelliptic curve of that genus. The abelian, its Jacobian is G dimensional. And well, it's very hard in general to write down equations for Jacobians. That's not how you think of them. You prove that they exist and you go from there. But over the complex numbers, it's easy to say what this Jacobian is. It's you embed the cyclotomic ring zeta L into G copies of C. There's a choice here, which I'm suppressing. There's a particular choice of how you embed it. But as a complex torus, this is the complex torus, one of the complex tori, which is Q adjoin zeta L mod Z adjoin zeta L. Zeta L, this is an Lth root of unity, tensor R. These are the abelian varieties that we're using. And I've run out of time, so I was going to explain a little bit of the proof, but the key thing is we use Selmer groups, and there's this very nice self map that these Jacobians have. They have this map 1 minus zeta L. Zeta L acts on this, 1 minus zeta L acts on this, and this is a degree L cover. And we use Selmer groups for this thing to show, on the one hand, that for certain n, the rank is 0, but at the same time, when you tweak the parameter by throwing in a q to the L, we'll just write down some points in a certain way. And in that way, you see that this related guy has positive rank. And it's just some yoga and abelian varieties that if you want to show that this, then it's actually just enough to show that for some n, this has rank 0, and then its twist here, q is the quadratic field, its twist has positive rank. That's enough. And so that's what we do. Okay, I'll stop here. Thanks.
Are there any questions for Ari?
I was confused about the reduction you were telling. You allow R to be a characteristic P, but then O can.
Oh, sorry. Yeah, maybe. Oh, I think actually she does even handle that. But yeah. Let me be careful. I should maybe say character 0, but I actually think she even handles that case.
But it's not Z in OK, which you will have then.
Yeah, but I'm not claiming. Yeah, I'm only claiming here for K a number.
Okay, well, let's thank Ari again.